So you have a data set and you have either a large number of categories that have an ascending or descending order, or you have a continuous explanatory or independent variable, or a number of other things. And very quickly, using a tool called regression makes sense. And let's say you have more than one explanatory variable or independent variable, then multiple linear regression makes sense. So today we're going to go over how to use multiple linear regression, how to code it from scratch using Python, and we'll also be going over an example of using it. My name is Jacob from Intrepid Protoworks. So we're going to kick off immediately with our imports. If you've been watching some of my previous videos, you'll be very familiar with why and where we use these. The one important new addition is that we're actually going to go ahead and use NumPy. The main reason is that multiple linear regression is most easily conducted using matrix algebra. The other thing that's going to be different from previous videos is that we'll be relying on both the T and F distribution. We will be using the T distribution to evaluate the significance of each individual independent variable, and we will be using the F distribution to evaluate the significance of the entire model. We have some boilerplate functions that we've developed in previous tutorials. We're going to go through those pretty quickly. The two videos to reference would be our video on the T distribution and our video on the F distribution. The first set of functions that we will need is our get mean, get sample variance, get sample standard deviation, get sample standard error, and get pooled standard deviation. These are prerequisites for calculating our T values when we want to evaluate the significance of our independent variables later on. Next up is our gamma function. We have used this in a bunch of videos in the past, and for additional information, you can go back and reference those. Next, we'll go ahead and define a function to get a p-value from a t-value. This is taking from a previous tutorial that looked at the t-distribution and t-tests. For more details on that, you can go ahead and reference that video. For the table that we use here, you can either pull it from the GitHub or generate it yourself from the t-test tutorial. Go ahead and make ourselves some more space and put in our f probability distribution function. We'll go ahead and follow that up with our function to get a p-value from an f value. We've covered both of these in our f probability distribution video. Now we are ready for our main function. So we'll go ahead and define multiple linear regression. It will take data alpha get p equals true and interaction test equals true for its arguments. Data is simply a list of lists this time. You're not using a dictionary. You can, though. You would just have to format everything a little bit differently. Alpha is just a float, which we'll be setting to 0.05 like usual. Get p and interaction tests are both booleans. So with the function definition done, we'll go ahead and define some empty lists and some starting variables. So we'll define one list called independence, and this will hold each of our x's. So in the example below, it will end up being education, age, and eventually something else if we decide to play around with it. Dependent, this will be our y value, and as an example, that will be income. Our observation count is just an iterator, and then we will calculate the number of independent variables, which we'll define as the length of the first row in our data set minus 1. The way we'll format the data is that the y values will be the first value in the list. That way we can pick them out for our calculations later on. And to get the number of x's, we will just subtract 1 from that, or the number of independent variables will subtract 1 from that. So in a lot of situations, if you have more than 2 independent variables, you'll be looking at wanting to calculate interactions. However, if you say have 3 independent variables, you end up with 3 two-way interactions and 1 three-way interaction. You have variable 1, variable 2, variable 2, variable 3, and variable 1, variable 3, and then variable 1, 2, and 3. So unless your hypothesis plans to look at all of those, you'll probably only want to look at specific ones because not all the interactions are going to make sense. So we'll go ahead and start off looking at how we do our interactions. So we have to calculate an interaction variable. We'll start off by doing an iterator, say I equals 0. And then we'll also do a Boolean, say, which we defined above. So we'll say if interaction test. and then we'll look at the number of independent variables. If it's 2, we'll go through each row in our data and we'll define our interaction term as row 1 times row 2. Remember, row 0, the 0th item in our row, is our Y data. And then we will append to the ith. So where we're at in the list, as we crawl through the list, we will append that interaction term. And then we'll go ahead and iterate I by doing I plus equals 1. We'll then go ahead and back out and say if the number of independent variables is equal to 3. We will then go ahead and loop through our data in the same way as above. And then we'll go ahead and copy and paste how we calculate the interaction term. However, we will go through and change each of these calculations to account for each of the different possible interactions. We'll say row 1 times row 2, row 1 times row 3, row 2 times row 3, and row 1 times row 2 times row 3. And each time we'll append this interaction term, and then we'll do plus equals 1 again. And you can do more complex interactions each time. This gets really harrowing in the research world if you start going through like 4-way interactions or multiple 3-way interactions, and you need a really good reason to do it. If you are uncertain whether or not you should be doing that, then do a really thorough literature search and try to get a grasp on what that would be, because a lot of times 4-way interaction terms or multiple different 3-way interaction terms gets really weird really fast. So now that we have calculating our interaction terms out of the way, we can go ahead and start in on our next part, which will be parsing our independent and dependent variables out into 2 separate lists. So we'll say dependent.append row 0. Remember, our dependent variable is our Y. So it's our outcome. It's what we're trying to describe the variance of. Now we need to build our list of each of our independent values. So however many X's we have, we'll start off by appending just a 1. The first column in our, what will soon be an array, will just be a column of 1s. And then we'll go through each value in each row, skipping the first one, so 1 colon, and then appending observation count dot append the value for that, and then we'll iterate observation count. And this gives us 2 different lists that we'll be converting to arrays. One is just our independence, and one is our dependence. So we'll say our independence is equal to a numpy array of itself, and then our dependence is also equal to a numpy array of itself. So np.array. So this is our first time bringing in NumPy. It's a really good and really powerful module. And if you've already familiar with Python data analysis, you've probably been screaming at the monitor, why haven't we been using it for a long time now? And again, the reason that we're not using it is because, simply put, it hasn't been necessary. It hasn't been worth the include. Now, that's something of an opinion, and you're welcome to disagree. There's a lot of people who will include it very quickly and use it very quickly. And there are some use cases where including it immediately is better, because NumPy is simply a really fast module that's really good at what it does. There's nothing wrong with it. I haven't been not including it because I have any kind of dislike. I just wanted to make sure we went over a lot of the steps in the statistical analysis. NumPy can also be a crutch sometimes. There are times I see it used where it's not necessary and it's not helpful. If you're doing a one-off analysis, it doesn't matter if it takes 0.5 seconds or 5 seconds if you're doing it once, and the overwhelming majority of your time is spent writing a report or writing a paper or analyzing those results or interpreting those results. Where speed of analysis matters is when the turnaround of those analyses is needed very, very quickly, and the amount of data coming in at a time is very vast. For example, marketing to customers via an online retail site like Amazon. They have to go through a lot of data very quickly, analyze that data, output results, and then algorithmically interpret those results, giving customers recommendations on what to buy. But that isn't our use case here, which is why we haven't included it until now. So we've converted independent and dependent into NumPy arrays. We then went ahead and created a new array called transposed independence by doing mp.transpose our independence. We then multiplied our transposed independence by our independence by doing mp.matmul or matrix multiply, and then transpose independence and independence. We then calculated the inverse of that. So the inverse of our transpose by independence by doing mp.linal or linear algebra dot inverse transposed by independence. We then multiply transposed by dependent, or we then do matmul again, transposed independence and dependence to create transposed by dependent. With all that in place, we can finally do our coefficients. So our coefficients equals numpy.matmul or mp.matmul inverse transposed by transposed dependence. Our coefficients are arguably one of the most important parts of multiple linear regression. So now that we have those, we can go ahead and calculate our fitted dependent values, which will then let us calculate our R squared and our F, and then also test the significance of each of our independent factors. So to calculate the fitted dependent values, we'll go ahead and start by making ourselves a new list. We will call it fitted underscore y's. Then we'll go ahead and do for row in data. Fitted y equals 0. Current IV equals 0. Then we'll go ahead and do inside this, we'll go ahead and do a for loop. We'll say while current IV is less than or equal to the num IVs, if current IV equals 0, so in other words, if we're looking at the intercept, we'll say the fitted y plus equals the coefficients current IV 0. And then else, in other words, if we're going through the coefficient for each of our variables, we'll say fitted y plus equals the row current IV times the coefficient of the current IV 0, of the 0th element of that. We need to do this because in working with numpy and making that into an array, because the coefficients is still a numpy array, which is basically a list of lists. So we have to reference that appropriately. We then iterate current IV plus equals 1, which will let us go through and hit up every coefficient in our list of coefficients. We then go ahead and append fitted y to our list of fitted y's. We'll go ahead and quickly fix an indentation error, make sure that the while loop is nested within the for loop. With a list of fitted y's in place, we can now go ahead and calculate our sums of squared total, our sums of squared regression, our sums of squared residual, and go ahead and prep for doing our F and R squared. We'll also need to get the dependent mean. We'll do that by doing mp.mean dependent. We will go ahead and make an iterator called I, then make a little bit more space so we can go ahead and start in on our for loop. We will make a for loop that loops through each row in our numpy array of our dependent values. So let's say for row independent, SS residual plus equals row 0. So remember, to access the value, have to take the 0th element in the row minus fitted y's, and then we'll take the ith element of that and then square it. And that all, as I said before, that all gets added to the sums of square residual. The sums of square regression plus equals fitted y's I minus the dependent mean squared. And then lastly, we iterate I by 1. Once that is done, go ahead and back out of our loop, and then we can define our sums of square total as equal to our sums of square residual plus our sums of square regression. With this, we can go ahead and calculate our R squared. R squared equals our sums of squared regression divided by our sums of square total. Now that we have our R squared, we can go ahead and get into the parts needed to calculate our F value. We'll start with the degrees of freedom for our residual, degrees of freedom for our regression. To calculate the degrees of freedom regression, we'll say DOF regression equals the length of our coefficients minus 1. Then we'll say the degrees of freedom for our residual equals the length of our data minus the length of our coefficients. With this, we can go ahead and do the mean square for regression, which is the sums of squared regression divided by degrees of freedom regression. The mean square residual is equal to the sums of square residual divided by the degrees of freedom residual. And with this, we can do our F, which will be F equals our mean square regression divided by our mean square residual. And with all of that in place, we can go ahead and calculate our P value for our F, which will be 1 minus get P from F. We'll take our F value, the degrees of freedom regression, then the degrees of freedom residual. Now we can go ahead and then evaluate if our overall model is significant or not. We'll say model sig equals false. And we'll say if PF is less than alpha, then our model significance is true. We'll go back up and add a quick equal sign to fix that error. Going back down, we'll go ahead and make a new empty list and we'll call it model data. And then we'll go ahead and define our intercept as equal to our coefficients, then our zero, our first row, and then the first element in that row. And then we will go ahead and add to our model data. So model data.append will say overall model intercept r squared f, the p-value for f if the model was significant, degrees of freedom regression, and the degrees of freedom research. With all of that in place, we can go ahead and start working on calculating a t-value for each of our coefficients. We'll start by creating an iterator I, and we'll set it equal to 1 this time. We're doing that so that it will skip past the intercept in our model. So we'll say, after that, we'll say for coefficient and coefficients, again, skipping the first element and going to the end. We'll say sums of square fitted equals 0. The sum of squares of our x equals 0. And we'll define x as an empty list. We'll say for row in data, x.append row, and then the ith number. And then we'll say x mean equals get mean x. So this gets us the mean of the independent value. So for example, the mean level of education, the mean age, I guess mean sex, though that doesn't really make sense. After that, we will say for row in x, sums of square for our x, plus equals row, or plus equals the row minus x mean square. Then we'll say for row in data, sums of square fitted plus equals the 0th element of our row minus the ith element of our row times the coefficient. Remember, we're in a NumPy array for coefficients, so we have to take the 0th element of that plus our intercept squared. The degrees of freedom for this will be the length of our data minus 2, like with other t-tests earlier. The standard error of our beta will be the sums of square fitted divided by the degrees of freedom, and then take the square root of that. So taking it to the power of 0.5 is the same as taking the square root. And then that is divided by the square root of the sums of square of our x. This gives us everything we need to get our t-value, which will be t equals the 0th element of our coefficient divided by our standard error of our beta. Now that we have that, we can get a p-value from our t-value. So we'll say p equals get p from t, and it'll be t and our degrees of freedom. And we'll say, and then we need to evaluate if it's significant. To do that, we'll say significant equals false. And then if 1 minus the absolute value of our p, because this is a t-test and p can be negative because our t-value can be negative. So if the absolute value or p-value is less than our alpha, then the significance equals true. And we'll go ahead and load all of this into our model data. So we'll say model data.append. Oh, we got to fix the coefficient error up top. So model data.append will do coefficient or t, or degrees of freedom or p, and if it's significant. And then we'll iterate I. And then going back, we have an error up top. We need to go ahead and pull or get p from t back 1 indentation level. So all that is left for us to do now is to return our model data. That will include our coefficients and the information on our overall model, as well as the significance of our overall model and the significance of our coefficients. With that, we can go ahead and do a quick example. We'll start with our standard procedure for opening up our data set. We've done this in many videos. If you want to see more detail about why it's done this way, you can reference some earlier videos. So say with open, our data set name, new line equals empty as new file, data equals csv.reader new file for row and data. If our row is not our header, and if the income is greater than 1 and the age is less than 65, we'll go ahead and add our y and then each of our x's. So this will be income, education, and age. So to do that, the last step is to take our dataset.append, and then we'll do int row 6, int row 4, and int row 1. Because this data set is not likely to be representative of what a lot of the people watching this video are working with themselves, we're going to go ahead and subsample this by first defining number of subjects. We'll just go ahead and set to 100 for now. And then we'll say data sample equals random.sample, and then we'll input our data set and the number of subjects. We'll also go ahead and define our alpha as equal to 0.05. We'll say our get p is true, so we'll be looking at getting our p values. And then we'll also say that we want to look at interactions. Before we go ahead and get our results, we're going to go ahead and say if interaction, and then we'll define a list of labels. We'll say income, education, age, and then education by age. If we do not look for an interaction, so else, our labels will be just income, education, and age. Then we will go ahead and define our results. So we'll say results equals multiple linear regression as defined above. It'll take our data sample, our alpha, our get p, and our interaction. With the results in hand now, we can go ahead and process and then do some output for those results. So we'll say if the overall model is significant, so the first row and then the sixth element in that row. So we'll go ahead and list out some of the parts of the overall model. So we'll start out with the p-value of the overall model. Go and round that to say 4 decimal places. We'll do the r-squared of the overall model. We'll do the f-value of the overall model. And then we'll go ahead and make a statement that the overall model was significant at alpha equals our alpha value, where f and our degrees of freedom values and our p. And then we'll go ahead and format that and put in the various parts of the results that are relevant here. So our alpha, results 06, results 07, results 03, rounding these as needed, and so on. Then if the model is not significant, we'll state that the overall model was not significant at our alpha. We'll also give the overall model p, the r-squared value, and the f value, because we'll still want to know that. And if any of these numbers are weird, it can also be an indication that the code has an issue. Now that we have the output for the overall model done, we can go ahead and start looking at the output for each of our independent variables. Technically, independent variables not really the right word. Typically something like explanatory variables is used because a lot of times we're looking at correlational data rather than data in an experimental setting that can properly infer causation. So to start off, we need to include a string that we'll construct in the following loop. This string will be a report of what is our model. So we'll start off with an iterator. We'll use 1 because we will want to skip past the overall model results. That is the first row of our results list. We'll then do a new line character, and then model. We'll say our label 0, which is our dependent variable, income in this case, equals, and then our intercept, and then plus. So that'll be the start. We will then say for row in results, skipping the first row because that's our overall model data. Model string equals the model string plus a plus sign plus the first element in the row, which will be our coefficient, times the ith label, which should correspond to the name of that variable. We'll then say if row 4, which will be what evaluates our significance. We'll print a new line character, and then for the label, it was significant at alpha equals our alpha value, where t and our degrees of freedom equals our t value, and p equals our p value. And then we'll do our label I, then alpha, row 2, row 1, row 3. Otherwise, else, if it's not significant, we'll do the end of line character or new line character. We'll say for our label, it was not significant at our alpha. And then we increment our iterator by 1. We'll then go ahead and print our model string. And that should just about do it. We should be able to configure and then run a new dedicated console and try running our code. So we have 2 issues. The first being that we misspelled format, and the second being that our p-value isn't making any sense. So we're going to go ahead and go back and print out our p-values at different stages and see what it looks like. So it doesn't appear that we got a whole lot of information from printing out our p-values. However, we can see that the report of our overall model is incorrect. It appears we forgot to actually report the f value that would explain it. So let's go ahead and add that in real quick. Now that we fixed that, we can see that the overall model print is outputting correctly. So now I'm just paging through the code real quick. So I'm going to scroll up here to the f probability distro function. Then I'm going to go ahead and paste in the code from my notes and check to see what I've done wrong. So I forgot to add taking it to the power of decimal df2. On the bottom line, I also forgot to add plus decimal df2. So decimal df1 plus decimal df2, and then take the square root of that whole term. If you run into issues where your output is not looking sensical, you can go ahead and reference the code. It will be up on the GitHub. So after making that change, we save and run again. We can go ahead and see that we're getting closer, but the output still isn't making sense. So we go ahead and try pasting in the original code. And now we are getting a value that's very close to 0. So that puts us into the range of where we expect to see these values. Now let's go ahead and go through, remove the print statements for our p-values, and then try running our code again. So now our results are looking pretty good. We're getting all numbers that make sense, all numbers that are within what we expect pretty well. We have some minor formatting errors like adding on errant plus signs and a couple other odds and ends, but really those are just things that can be tweaked around and will probably need to be tweaked around for each person on their own, depending on how they need to have their results. We also have some sort of bug where it's saying that our coefficients are not significant when they should be significant. So we need to look at why that is happening as well. However, for now, let's just go ahead and try adding another variable and see how that works out. Whether or not it shows up proper in the code for whatever reason, we're getting results that are making sense and we're getting output that's making sense. So what we'll do is we'll adjust how our output works, add in a new variable, and see how things look from there. So first we're going to go ahead and print off the header of our data set. That way we can see which variable we want to add. So let's go ahead and add sex as a variable. We can just simply do that by appending a new variable at the end of the data set. We'll go and comment out that line and then add in int row 0. Go ahead and add in sex as a variable down here and then save and run. Now that we have sex being included, let's go ahead and print off some data in this else statement. That way we can see our t-score and our p-value and our degrees of freedom. So do our t-score degrees of freedom equals our t-score, and then also print off our p-value. And we'll format in the same way that we formatted above. So we can see that sometimes our results are significant, sometimes they're not. Remember, one of the things that we're not taking into sufficient account for this to be real, quote unquote, is the amount of power needed to look at things that are so wildly variable as income. So we're going to go ahead and just output the information for the t values, and we're going to try to do some diagnostic stuff. We're not going to spend a whole lot of time on this because this output isn't that important other than the actual numbers themselves, the t-scores, degrees of freedom, the p-values, etc. So let's check if the bool is being outputted correctly, or if and double check that we're calling the correct variable. It appears that we are. Let's double check our code up here. So I'm going to go ahead and paste this in from my notes, double check everything's the same. It looks the same to me. If you see something different in the comments, say something. Double check this part here. Still looks the same. I'm not sure where the problem is. There's no typo in the alpha value. We'll print our p values for each of our coefficients. So the first two are less than our alpha value. Let's go ahead and double check the code's the same here. Yeah, the code looks like it's still the same. I didn't have any typos there that I'm seeing. Go ahead and run it again. Yeah, we're still looking at that same issue. I'm sure I'm staring right at the problem as to why it's not properly showing up as being significant. If you see what it is, toss something into the comments below. You have this weird issue where things are not rounding as well. Let's go ahead and save and run without the -1 of the absolute value of p. Yeah, that's something weird. So that seems to have done something. So let's continue. It's probably just an issue with the fact that t values can be negative and positive, and the resulting p values can also be negative and positive. Let's go ahead and add in some additional labels for interactions. So we have education by age, education by sex, double checking the amount of interactions we should have. We have age by sex, and we should have education, age, and sex. We're getting a index out of range error. That's probably an issue with the labels, but I'm not sure where. It's really interesting to note here what we have going on with our interactions. Like, this is just a academically interesting finding. Like, we have a statistically significant three-way interaction. So age, income, and sex interact in a specific way. We're not going to go into too much details on this. We can start looking at that interaction by outputting graphs and whatnot, but that's outside the scope. This video's already gone on for a long time. So it looks like we're outputting all of the parts, but it's telling us the index is out of range, and I'm not sure why that is happening. Again, if you see it, toss a comment in below. And double check the formatting here. Let's go ahead and also output the coefficient so we can see what the coefficient is. Oh, we forgot to add the curly braces. Let's save and run that again. So getting our coefficients. Oh, now they're showing up as significant. So now we're not getting our coefficients. So let's go ahead and put this up top and add this into our if it's significant part. It could be just that using logic like this doesn't necessarily isn't that good of an idea. We just probably need to make the logic a lot more complicated. Our coefficient values are pretty big. That could be just the random sample we got. Again, incomes can be really variable, and because of that variability, we can end up with some pretty weird samples sometimes. So that should about do it for this video. We should cut off here. If there is an interest, I will continue to elaborate on multiple linear regression. Make sure to let me know in the comments below, and make sure to let me know if there's an interest by liking and subscribing.